Today we will analyze the effect of air resistance on a stack of coffee filters that is moving through the air. I am joined today by Giselle and by Isabel. Thank you very much. Here is a stack of coffee filters. I'm going to drop these filters above a motion detector, which is connected to a LabQuest. This will allow me to measure the position and velocity of the stack of filters as it moves through the air. Let's start our measurement now. Now let's analyze our data.
Let's look at a graph of position versus time. Here I am plotting position on the vertical axis and time on the horizontal axis. Here's what we get. The position starts at 0 and it increases as time increases. The slope of the line begins at 0 and the slope increases, and eventually, after about 0.9 seconds, it reaches a constant value of slope. If this was a case of constant acceleration, we could apply the kinematic equations. This is what we would get. We started at a velocity of 0, so the position x is given by a half gt squared, where g is the acceleration due to gravity. Let's plot that on these axes. The red curve is the theoretical curve, 1/2 gt squared. You can see that the position which was measured is less than the theoretical value. This suggests that our acceleration is something less than g. It is less than 9.8 meters per second squared. Now let's look at the velocity. Here we plot velocity on the vertical axis versus time on the horizontal axis. Here's what we get. The velocity starts at 0 and it increases. The slope of the tangent to this graph is decreasing as time increases. It's high here. As you go along, it gets lower and lower, and eventually it becomes 0. At this point, we have constant velocity. If we applied the kinematic equations to this problem, and if we had constant acceleration, this is what we would get. V equals gt. Here's that plotted on these axes. The blue line is a graph of V equals gt. It has a constant slope. What we notice here is that for velocity versus time, the measured value, the slope is not constant. The slope is decreasing as time increases. Since the slope of the tangent is the acceleration, we conclude that the acceleration is decreasing as the object falls. Why does the acceleration decrease? Giselle, this is a question for you. Yes, you're right. It decreases because there are two forces involved. We have the force of gravity, but we also have another force called the drag force. Gravity acts down, but the drag force acts up. The drag force is a velocity-dependent force that opposes the motion of an object as it moves through a fluid such as air or water. Here's a free body diagram. This dot represents the coffee filter. There's a force of gravity acting downwards, Fg, and the drag force acts upwards, Fd. It acts opposite to the direction of motion, and it depends on the velocity. The acceleration is down, and let's apply Newton's second law to this problem. And we'll take the x-axis to be downwards positive. The net force is Fg minus Fd, and that equals mass times acceleration. At the start, v equals 0, and Fd is equal to 0. So this equation becomes Fg equals ma, or mg equals ma. And the solution is that A equals G equals 9.8 meters per second squared. But when V increases, Fd increases. And that is going to decrease the net force, which will decrease the acceleration. And eventually, the net force is going to be 0 when the drag force equals the force of gravity. In that case, the acceleration is 0 and v is a constant value. And that constant value of v at the end is called the terminal velocity. Here's a graph of velocity versus time for the coffee filter. As you can see, the acceleration or the slope of this graph is decreasing with time, and eventually the slope becomes 0. At this point we have 0 acceleration and constant velocity. I took an average of these values of velocity and I got 1.51 meters per second for the terminal velocity. Causes of the drag force. There are two types of drag forces. One is called the inertial drag, and that's due to inertial forces. The moving object pushes away the fluid in front of it. This force depends on the mass of the fluid which is pushed away. And in this case, there is turbulent flow of fluid around the object. And an example of this would be a ball moving through the air. And then there is viscous drag. It is due to viscous forces. Viscous forces are between the fluid molecules and the surface of the moving object. There is laminar flow of fluid around the object when we have viscous drag. An example of this would be dust slowly sinking in a liquid. Reynolds number. In order to determine whether or not we have viscous drag or inertial drag, we need to look at the Reynolds number. The Reynolds number is a ratio of the inertial forces to the viscous forces. And it can be written as rho VL over eta, where rho is the density of the fluid, eta is the viscosity of the fluid, v is the speed of the object, and L is the size of the object, such as the diameter of the coffee filters. If the Reynolds number is high, greater than 1,000, we have inertial drag. If it is low, less than 1, then we have viscous drag. If it is between 1 and 1,000, then it may be a combination of the two. Let's look at the inertial drag force. We have inertial drag for high Reynolds numbers, greater than 1,000. We can write it like this. Fd equals 1/2 CD rho AV squared, where CD is a drag coefficient, and it depends on the object's shape. Rho is the density of the fluid, A is the cross-sectional area of the object, and V is the speed of the object. Note that the inertial drag force is proportional to the square of the speed. Let's look at the drag coefficient. CD. Here are the drag coefficients for different objects in order of increasing drag coefficient. For a dolphin we have 0.0036. Fighter aircraft, 0.016. 0.23 for a car. 0.5 for a sphere. A cylinder traveling lengthwise, like this, it's 0.8. And for a cylinder traveling sideways, like this, it is 1.1. Now let's look at viscous drag. We have viscous drag for low Reynolds numbers, less than 1. And we can write it like this. Fd equals Bv, where B is a constant which depends on the size and shape of the object and viscosity of the fluid, and V is the speed of the object. Note that for viscous drag, the drag force is proportional to the velocity, whereas it is proportional to velocity squared for inertial drag. For a spherical object of radius r moving in a fluid of viscosity eta, we can write the drag force like this. 6 pi eta RV. where r is the radius of the object. Let's calculate the Reynolds number for a few cases. The Reynolds number is rho VL over eta. Here's the density and viscosity for different fluids. For air, the density is 1.293. And for liquids such as water, olive oil, and honey, it is much higher, up to 1400 for the honey. For viscosity, for air, it is the lowest, 1.8325 times 10 to the negative 5. Then it is larger for the liquids, 1 times 10 to the negative 3 for water, up to 84 times 10 to the negative 3 for olive oil. Let's look at the case of air. Reynolds number could be written like this. We have the density of air, 1.293, times V times L, divided by the viscosity of air, 1.8325 times 10 to the negative 5. And this becomes 70559 times V times L. Note that when V increases and when L increases, we are more likely to have inertial drag. Let's look at our coffee filters. And we'll say V is 0.2 meters per second. And the L is 15 centimeters, or 0.15 meters. Let's put in the numbers. Reynolds number is 7055 times 0.2 times 0.15, and we get 2117. This is greater than 1,000. So this is inertial drag. Now let's consider a smaller object. Let's take a grain of pollen moving in air. We'll give it the same velocity as a coffee filter, 0.2 meters per second. The L now is the diameter of that grain of pollen, which is, for instance, 20 micrometers. Putting in the numbers, 70559 times 0.2 times 20 times 10 to the negative 6 gives us 0.28. This is less than 1. So this is a case of viscous drag. Note, we have a much smaller length for the pollen than we had for the coffee filter. So we had viscous drag for the pollen. Our next topic is pollen falling through air, an example of viscous drag. To learn more about this topic, click on the next video in this series, Viscous Drag.